Hey guys, so today we're going to talk about acceleration near the Earth's surface. It's exactly probably what it sounds like, is we're including gravity now. So it's the same as free fall acceleration, might be another way that you've heard that term. So what we're looking at is basically how gravity comes into the mix, and then how that can affect when you're calculating velocity, and you can use your other equations to calculate distance, time, and other things like that. So we know that when something is allowed to fall, it's going to experience acceleration due to gravity. We know that gravity is a thing that exists, right? Gravity has a value attached to it on Earth, and gravity is going to be just slightly different anywhere around the world, because we know that at different elevations, gravity would be just tiny bits different. But in physics, we're going to say in general that gravity is 9.8 meters per second squared. Okay, so gravity is an acceleration. So it's going to be represented by the variable g, and this is a constant. Okay, so anytime you see a lowercase g, it's representing gravity, which is 9.8 meters per second squared. Okay, so when we use it as a vector, so if we need to designate a direction, gravity is going to be defined in the negative direction. Okay, so you can say that it is a positive 9.8 meters per second squared down, or you can designate and say that it is negative 9.8 meters per second squared, if down is already assumed. So the value for g cannot be used at super high altitudes, like I just mentioned. So like at the top of a mountain would have just a slightly different gravity value, and obviously not on different planets, because gravity is not the same everywhere. That's why you can float around in space and on the moon. Okay, so when we talk about gravity, we're using 9.8. This is going to be true for any object, no matter how big or small it is, and when it's not experiencing air resistance or other force. So for our purposes, we are going to assume that there is no air resistance, and we're going to assume no air resistance on most things all year long. So that said, basically we're going to treat things as if they're falling in a vacuum. Okay, so for examples for this, you might be wondering, some of these, and actually all of them, we're going to use the 5 equations of kinematics that we looked at last class. Okay, so those 5, where you could choose through the 5 equations and they all had one variable that was different, we're going to use those same ones here. And so as you can guess, the acceleration will be gravity. So in this example, a cat knocks a flower pot off of a ledge. The flower pot hits the ground 2.7 seconds later. How high above the ground is the ledge? So how high is something? So we're finding the distance. We're given the time, and we know the acceleration of gravity is going to be 9.8 meters per second squared. So following the same strategy here, we drew a diagram. We have a cat, he knocks it down. The initial velocity was 0 because this pot was sitting still initially. Then the cat pushed it off. It hits the ground, and we don't know what V2 is, but we know that it hits the ground after 2.7 seconds. And then the acceleration is going to be 9.8 meters per second squared down. And since, if you look over here, our positive is designated as down in this case because it's starting up high and it's landing in the bottom, you will enter in acceleration as 9.8 meters per second squared, not negative in this case. So when you plug this in, and I'll tell you why in a second. So when you plug all this in, we're going to pick equation 3 because we have the distance, we have the initial velocity, the time, we have acceleration. I'm sorry, I just completely said that wrong. I apologize. We're solving for distance. We do have the initial velocity, the time, where we have the acceleration, and then obviously the time again. So we plug that in, we're still solving for distance. We'd have 0 meters per second times the time, plus 1/2 times gravity times the time squared. So what you end up with here is 35.721 meters. And if you're using sig figs, you would round that up here and say that the ledge was 36 meters above the ground. So the thing with the positive and negative here, if you leave this as a negative, your answer just ends up being negative, right? So since we are trying to figure out, we know that the distance would have been traveling in the negative direction, okay, because this cat pushed it down. Since it's traveling in the negative direction, the answer would have shown that it was traveling down anyway. So if you designate this as negative here, the answer turns out being negative. A distance, if we're just looking at distance, can't really, you can have like just a negative distance. You'd have to have a positive distance either way. So the negative in front of this would have only designated that it was going up or down, which we already know it's falling down. So we can leave this in here as a positive since the direction is negative, and this indicates, the negative indicates that it is going down. So for another example, objects experience acceleration due to gravity even when their initial velocity is upwards. Okay, so example, if you toss the ball in the air, the ball experiences gravity the whole time, right? Like gravity doesn't just stop. So in this case, if you have tossed something up in the air, acceleration is always going to be negative 9.8 meters per second squared. Okay, so it's negative because we have it's moving away from the earth here, and then it's falling back down and following it. So as the ball moves upwards, it's going to experience acceleration down, slowing it down until it stops just for a second here at the very peak. Gravity continues to accelerate downward even as the object is falling. So in this example here, and a tennis ball is tossed from your hand 1 meter above the ground with a velocity of 3.6 meters per second up. What is its maximum height above the ground? So this is kind of a complicated, no, it's not really complicated, but you do need to pay attention. So it says that you're tossing it from 1 meter up. So your hand is already 1 meter above the ground. So that its initial position there would be 1 meter. So then you toss it upward with an initial velocity of 3.6 meters per second up. It stops periodically just for like a second right at the peak. So the V2 is going to be 0. We want to know how far that was. What's the distance there? So in this case, we're tossing it upward. Our positive will be up. So we have our initial velocity, final velocity, acceleration of negative 9.8 meters per second, and you're finding your distance. So we're going to use this equation for that. So this is equation 5, I believe. So we'd have the final velocity squared equal to the initial velocity squared plus 2 times acceleration times the distance. So when we plug all that in, they're choosing to rearrange this equation first. You do not have to do that. So if we plug in all of our values and we're solving for distance, you're going to end up with that it's moving 0.661 meters. This is the distance. That's not our total distance, okay? So the question is asking, what is the tennis ball's maximum height above the ground? Well, if you started at 1 meter above the ground, you're going to have to add this distance to your starting position, okay? So your starting position was 1 meter plus this new distance that we just calculated for a total maximum height from the ground of 1.7 meters. So another misconception that happens really pretty often is that objects have a final velocity of 0 as it hits the ground. Okay, so we dropped a ball and when it hits the ground, its velocity is 0 because it's stopping, right? That's not true. So think about it this way. If you were laying on the floor and someone dropped something on you, obviously the velocity is not 0 because it would hurt, right? So if you're laying on the couch and your little brother jumps on top of you, his velocity is not 0 when he hits you. He still has velocity because then he applies his force to you. So we want to always take that into consideration, that even if you toss something up and it lands, its velocity is not 0 when it lands. So here's an example that would use that. What is the tennis ball's velocity right before it hits the ground? So if we're looking at the question from before, we talked about we tossed the tennis ball up in the air. Okay, so our initial position here when it hits the ground is going to be -1, because remember we had the hand. Here, I'll just go back to it. Okay, so the initial position was at +1 meter. So if we're saying what's the velocity when it hits the ground, well, now I am -1. I'm 1 meter below where I started. So that's why that initial position or our distance that we went here was -1. So from the hand to the ground was 1 meter. The velocity is going to be, the initial velocity was 3.6 still. The acceleration is still the same as gravity. So what is our final velocity as it hits the ground? So in this case, actually all we're really doing is changing the distance here. So we're using the same formula. We still have velocity, final velocity squared is set equal to the initial velocity squared plus 2 times gravity times the distance. Okay, so here you're just paying attention that these are negative. Both these are negative because the position's negative because you are ending lower than where you started, and gravity is negative because it's pulling it downward. So when you guys do this, you're going to end up with a plus minus, you know that here. So since the velocity is downward, you would choose the negative root. Even if you don't go so far as to actually write that down, you do know that the velocity should be downward because it's falling. Okay, so you toss the ball out of your hand, it goes up, and then it falls down past your hand and hits the ground. So that we know now the final velocity is going to be 5.7 meters per second down. And that's it. So please refer back to the page. Go back here with your 5 equations of kinematics, so that we talked about last class. And you're just basically using these same equations, these equations here, and substituting the acceleration value for gravity. Okay, so gravity is going to be negative 9.8 meters per second squared. The only time that would be a positive value is if you're talking about something just falling straight down to the ground with no initial upward force. So please, again, use these as needed. Make sure you're reading your questions carefully, drawing your diagrams, labeling things, figuring out what you know, what you don't know, and what equation to pick. And then you guys do have some practice to complete today. So another quick reminder is that we do have our test coming up. It's going to be on 9/23 and 9/24. So please let me know if you guys do have any questions, and we will set aside some time to conference, or we can talk over email or whatever works for you guys. So just let me know. Hope you guys have a good day.